questions 21 through 25 on the 2010 Grade 10 AMC 10A. The polynomial x to the power 3 minus ax squared plus bx minus 2010 has three positive integer zeros. What is the smallest possible value of a? In this question, we are going to use Vieta's formula, and there's many variations, but in this particular question, we have a polynomial of degree 3. So it's of the form, and these letters might get a little confusing, but just bear with me. Ax to the power 3 plus bx squared plus cx plus d. If you have an equation of that form, the sum of the roots is equivalent to minus b over a. And the product of the roots, in this particular form, where it's x to the power of 3, is minus d over a. So that's what we're going to use on this equation right here. And our equation is x to the power of 3 minus ax squared plus bx minus 2010. So the sum of the roots would be minus b over a. So in this case, it is minus a over 1, which is just a. So this is the sum of the roots. Now, they're telling us that there's three positive integer zeros. It's another way of saying that there's three roots. So I'll call those roots R1, R2, and R3. And the sum is equal to a, like we just figured out. Now the product of the roots, we're going to use this formula. So the product, which in our case would be R1 times R2 times R3, is minus d over a applied to this guy. So that would be minus 2010 over 1, and that's just 2010. So basically what this means is that we have to figure out three numbers that when multiplied together equal 2010, and then we then add those three numbers up to get a. But they want the smallest possible value for a, so we can't just choose anything. So of course we have to first break up 2010 into its prime factors, and that's 2 times 3 times 5 times 67. And we have to get the smallest possible value for a. Okay. So I'm going to keep this 67, because if I multiply it by anything, it's going to become pretty big really quickly. So that will be sort of my R3. And then my R2 and R1, I've got to choose them in a way so that it minimizes a. So I've got a few choices here, right? I can choose, let's see, 6 and 5. I can choose 10 and 3. And I can choose 2 and 15, I believe. And which one of these would minimize the sum of R1 plus R2 plus R3? I believe it's the first one. So it would be 6 plus 5, which is 11, plus 67, which is 78. And that's it. So number 21 is A. 8 points are chosen on a circle and chords are drawn connecting every pair of points. No three chords intersect in a single point inside the circle. How many triangles with all three vertices in the interior of the circle are created? Here's our circle. And generally speaking, the way it works is that we have to select three chords, obviously, right, to make this triangle. So, for example, we'd have something like, let's say this chord, a chord like this, and a chord like that. And if we do, as I hope you can clearly see, a little triangle has been formed. According to the question, that all three vertices are in the interior of the circle, and they are. So they're asking how many of these can we create? All right. Well, we obviously must select three chords. And these 3 chords involve 6 points. 2 points for that chord, 2 points for that chord, and 2 points on the circle for that chord. So really just each selection, like the one I just drew, produces one triangle in the interior. So the total number of such triangles really involves choosing from the 8 points in the on the circle. You have to choose from them 3 chords. So how many ways can you choose 3 from 8? Well, it's 8 choose 3, and that is 28. And that's it for number 22. So the answer is A. Each of the 2010 boxes in a line contains a single red marble, and for 1 less than or equal to k less than or equal to 2010, the box in the kth position also contains k white marbles. Isabella begins at the first box and successively draws a single marble at random from each box, in order. She stops when she first draws a red marble. Let P at n be the probability that Isabella stops after drawing exactly n marbles. What is the smallest value of n for which Pn is less than 1 over 2010? So we have a whole bunch of boxes, 1, 2, 3, 4, all the way up until 2010 boxes. Now, in each box, there is one red marble. So this one will have 1, this one will have 1, and so on. All of them will have 1 red marble. But there's white marbles in each of them, but the number depends on which box it is. So if it is the first box, there will be 1. If it is box number 2, there will be 2 white marbles. If it is box number 3, there will be 3 white marbles, and so on. So 4, 5, 6, 7, all the way up until 2010. So now what we have to do is figure out P at n. P at n is the probability that you, or Isabella, I should say, draws a red marble. So let's just talk about it for each of these for the first few, and then we will get some sort of a pattern, and then we can extrapolate that to any value of n. So how does she get in the first box a red marble? What is the probability? Well, the probability is 1 out of 2. There's 2 marbles, one's red, one's white. The probability of choosing a red one is 1 out of 2. So that's pretty straightforward. Now let's look at the second one. What's the probability of getting a red marble here? Well, remember, she is doing this in successive form. So she does the first box, and then she picks from the second box, and so on. So if we have not reached a red marble yet, we have to take that into consideration. So we did not get a red marble in the first box. So that means the probability of that happening is a half. We got a white marble, let's say. Well, that's the only other choice. And then we have to multiply that by the probability of getting a red marble here. And that would be 1 out of 3. Okay, and that is, of course, 1 over 6. In a similar way, let's talk about box number 3. Box number 3, we did not get a red marble in box number 1. The probability of that is 1/2. We again did not get a red marble when we were choosing from box number 2. The probability of getting a white marble is 2 over 3. And then now we get a red marble, and the probability of that happening is 1 over 4. And that is, of course, equal to 1 over 12. So I'll do one more, and hopefully you'll be able to see the pattern. That's for box number 4. For box number 4, again, for the first box, you did not get a red marble. Probability of that happening is a half. Second box, you did not get a red marble. The probability of that happening is 2 over 3. Third box, you again did not get a red marble. You only got a white marble. Probability of that is 3 over 4. And then now finally, you get the red marble, which has a probability of 1 over 5. And this is equal to 1 over 20. So I hope you can see that if you're doing it for the nth box, let's say there's some box and it is n, how would we calculate that? Well, it would be 1/2 times 2/3 times 3 over 4 times 4 over 5, like that, times ... until you get to n minus 1 over n, and the very last one will be 1 over n plus 1. So that is our formula. I'll write it out here again. And there you go. And we want this to be less than 1 over 2010. So this should be pretty straightforward to figure out. Now the good news is that, and you probably already figured this out by looking at this, is that a lot of this cancels. You see how all these guys cancel? And that canceling will continue until you get to the very end. And the only thing that's left at the very end is just n times n plus 1. And that has to be less than 1 over 2010. So you flip it, and if you do, you get n times n plus 1 greater than 2010. Now, you have a choice here. You can do a quadratic, or you can just do inspection. What I did was I took the square root of 2010 just to kind of get an idea of what kind of range am I in. And if you do, you get approximately, 43 or 44? I think like 44. So that means that n has to be somewhere around that. So let's just try some numbers. Let's try 45. If n is 45, you're going to have 45 times 46. And is that greater than 2010? And it is, because that is equal to 2070. So let's see. If n equals 45 is one of the answer choices, it should be. And it is. So number 23, the answer is A. The number obtained from the last two non-zero digits of 90 factorial is equal to n. What is n? Well, 90, the number, we have to figure out how many times is it going to be divisible by 5. Well, there's 18 numbers from 1 to 90 that are factors of 5. And then I also have to take into consideration factors of 25, because those give me 2 factors, and there's 3 of those guys, 25, 50, and 75. So together, I've got 21, 18 plus 3, 21 factors of 5. So 90 factorial can be broken up into 5 times to the power of 21. Now, in terms of powers of 2, there's many of those, right? Because 90 divided by 2 itself is 45, and then you have to look at powers like 4 and 8 and 16. There's many of those. So I don't really need to worry about that. I just wanted to write 2 to the power of 21 and feel comfortable that I can do that, and I definitely can, because there's more than 21 factors of 2. And then, of course, some n. I don't know what that n is. So that is a very quick way of breaking up 90 factorial. And then the good news is that because these exponents are the same, I can combine them, the bases I should say. And that means that 5 times 2, which is 10. So 10 to the power of 21 times n. So that means that you've got this number n, I don't know what it is, but some number, and then it's followed by a whole bunch of zeros, and there's 21 zeros. So that is the nature of 90 factorial. Now we have to break up 90 factorial into 2 components, which I will call A and B. The first, A, is going to be anything that is not a multiple of 5. And B will be anything that is a multiple of 5. So I'll list the B's first because those are easier. So for example, you got 5, 10, 15, and 20. And then you have, of course, the next few, and I'll write them all out. So there you have all the factors of 5, and then an A, this guy, that's going to be everything that's remaining. So for example, we got 1, 2, 3, 4, those numbers, and then of course the next ones from 6 to 9, 6, 7, 8, 9, and so on, all the way up until the very last one. And I'm not going to write all these out because there's too many of them. But the very last one, of course, would be 86, 87, 88, 89. Now, at this point in the question, we are going to utilize something called mod. And if you're not familiar with it, I'll give you a quick primer. If you have something written as A is equivalent to B mod N, what does that mean? It means that if A and B have the same remainder when they are divided by n. A and B have the same remainder when they are divided by n. Let's give an example. For example, 27 is equivalent to 52 mod 25. And why is that true? Well, 27 divided by 25 gives a remainder of 2. 52 divided by 25 gives a remainder of 2. So this is a correct statement. So what we have to do is apply mod all over this question. And in particular, we're going to use mod 25 because that will help us the most. So first, let's look at A, which is this big long one right here. If we look at A, mod 25, well, what is this equivalent to? It's 24, right? Okay, 24 in terms of mod 25 is, well, it's -1. But did you understand that, yes or no? If I take 24 and I divide by 25, what is the remainder? Well, the remainder is 24, but you can also write it as -1 because -1 plus 25 is 24. So that's this guy right here. What about this one? That is equivalent to 3024. I'll just write that in there. And 3024 mod 25, if you divide that by 25, the remainder is 24 again. But 24 can be written as -1 instead of writing 24. And all of these have the same. If you do this one, you will see that that is 24,024. And yet again, if you take the mod of 5, the remainder is 24, but 24 can be written as -1 in the world of mod. So all of these become -1s. And how many are there? Well, it goes all the way to the end, this guy. And there are 89, but there's sums of 4, right? So 18 of those. So this whole thing really combines, if you're looking at just A, to then just -1 to the 18. And that is, of course, mod 25. Don't forget that. And -1 to the 18 is just 1. So we have 1 mod 25. All right, so far so good, I hope. Trying to do this slowly so that you understand. Now let's concentrate on B. B is this guy right here, this big long thing. And B is actually, well, I don't know. I was about to say it's a little bit simpler, but perhaps it's the same. B, again, we're going to do the same kind of thing. But first, before I do that, I'm going to factor out 5 from everything. And if I do, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, right? Because those ones involve two factors. So it's 5 to the power of 21. Now what's left is just these guys, just 1, 2, 3, 4, 6, 7, 8. And there's not that many of them, so I'll write them all out. And there you go. So now we use the same type of story here. And the first thing I'm going to do is just kind of bring this 5 to the power of 21 over here, because I'm really just interested in these numbers here. So here we go. Let's apply the whole mod thing. This is 24. So that, if you do the mod of 25, as before, is negative 1. And in a very similar way, you'll see that this is also negative 1. And this is also negative 1 when you take the mod of 25. But this is a little bit different though, because that's not the same. We'll do this individually, each number at a time. 16 mod 25 is negative 9. 17 mod 25 is negative 8. 18 mod 25 is negative 7. And then you've got this 6 mod 25, which is just 6. And don't forget the mod 25. So there we go. So now we got to combine all of these, and if we do, let's see what we get. These three combine to give negative 1 to the power of 3, which is just negative 1. These four combine to give, I'll just write it here, which give a remainder of negative 24 when you divide by 25, and that is equivalent to 1, because negative 24 is the equivalent of 1 because you add negative 24 to 25. So this just becomes 1, and that's mod 25. So this is just negative 1 mod 25. And that is b over 5 to the power 21. All right? So far so good. We've got a is equivalent to 1 mod 25. And we've got b over 21, 5 to the power of 21, is equivalent to negative 1 mod 25. Now, we have to start looking at 2 to the power of 21. Because if you remember at the very beginning, I had broken down 90 factorial into 5 to the power of 21. Times 2 to the power of 21 times some big long n, and that allowed us to conclude that this was going to be some number multiplied by 10 to the power of 21. So some number followed by 21 zeros. So now let's look at 2 to the power of 21 with regard to mod 25. You do a little bit of manipulation here, and you get the following: 2 times 2 to the power of 10 squared. 2 to the power of 10 can be easily figured out. That's just 1024. Now if we start doing mods, and I've got to remember to use the right symbols here, I have to use the 3 equal signs, or triple, like this. If we start using mods, obviously when you take the mod of 1024 in terms of mod 25, the remainder is 24, but we write that as negative 1. So this becomes negative 1 to the power of 2. And 2 mod 25 is just 2. So that is equivalent to this. And this becomes just 2, because negative 1 squared is just 1. So there we go. But we don't like this 2 here. If you notice up here, we got a negative 1, and up here we got a 1. In mod questions, it's always good to get 1. So how can I get 1? Well, if I multiply both sides by 13, that would give me a 1 as follows. I'll show you. This would become 13 times 2 mod 25. Well, 13 times 2 is 26. And what's 26 divided by 25? Has a remainder of 1. So there you go. And this will be beneficial a little bit later on. I just had to add that 13 in there. So now we're into the final stages of our question. I will write n is equivalent to this guy right here, 13 times 2 to the power 21. N, and that's the mod of 25. Now, this part here is very similar to what we have up here. If you notice, if you manipulate that, you'll be able to write that as the following. It will be 90 factorial over 5 to the 21 factorial. And that is, of course, mod 25. Now, this guy right here, we had earlier figured out what that is. That is equivalent to a times b. And we've got this 5 over 21, because remember I had broken up 90 factorial into a times b. And a mod 25, we had figured out earlier, was 1. And this b over 21, 5 to the power 21, mod 25, is negative 1. So instead of the a, I can put just 1. And this whole thing we got earlier was negative 1 when we were doing mod 25. So this just becomes 13 times 1 times negative 1, which is negative 13. And remember, negative 13 is equivalent to 12 because you're dividing by 25, so 25 minus 13 is 12. And that is our final end product. So that concludes that 90 factorial, when you divide by 25, has a remainder of 12. So therefore, the last two digits that are not zeros of 90 factorial will be equivalent to 12. So the answer to this big long question is A. And I also want to provide the official solution that I encourage you to read to get a better understanding if what I explained didn't make that much sense to you. Jim starts with a positive integer n and creates a sequence of numbers. Each successive number is obtained by subtracting the largest possible integer square less than or equal to the current number until 0 is reached. For example, if Jim starts with n equals 55, then his sequence contains 5 numbers. 55 minus 7 squared, then that's 6, then 6 minus 2 squared, which is 2, 2 minus 1 squared, which is 1, and then 1 minus 1 squared, which is 0. Let n be the smallest number for which Jim's sequence has 8 numbers. What is the units digit of n? This question, the general rule is that you're taking some number and you are going to add to it some square. And that must be less than n plus 1 squared. So for example, when we had 6 as our a, we had to add this 7 squared, right, in order to get 55. And when we did, you got 49 plus 6, which is 55. And 55 is less than n plus 1 squared, which would be 64. So that's the only way this can work. So we have to apply this general rule, but we have to go in reverse, and that will allow us to figure this out. So I have to have 8 numbers, so I've got to go from A8 all the way back to A1. So A8 all the way back to A1, A7, A6, A5, A4, A3, A2, and A1. And A1 is what I'm interested in. That is the number that is our n, I guess. So the only way we can do this without an enormous amount of guessing is to fully understand the general rule. So this is our general rule. This was just an example. So that means a plus n squared is less than n squared plus 2n plus 1. The n squareds cancel, so that means a is less than 2n plus 1. And therefore n, if you isolate for it, it would be a minus 1 over 2. That n is greater than. So let's work with this. We have to end with the 0, right? That's the criteria. Until 0 is reached. So my A8 has to be a 0. Now we start employing this rule. How do we get to a 0? Well, just as before, we had to have taken 1 and subtract from it 1 squared in order to get 0. They even give you that up here. So it kind of helps you out a little bit. Okay, no problem. How about A7? Well, A7 obviously was 1. Okay, and how do we get that? Well, we just did the same thing they did up here. 2 minus 1 squared. So that the first few are pretty straightforward to get 1. Okay. Now, what will be my A6? Well, the A6 is right here. That's A6. How did I get that, though? Well, how did I get A6? Well, I think I can get that pretty straightforward, in a straightforward way, by just going 3 minus 1 squared. So far, its numbers are pretty small. So that means that my A5 is 3. Now, at this point, we can continue to do it in terms of inspection, but since the numbers are getting a little bit larger, I'd like to apply this formula. I didn't think we really needed it until now. Now, this number represents my A. And this square that I'm going to put in here, like I had done up here, that's going to represent my n. So this formula allows me to figure out what I can make my n. If a is 3, it would be 3 minus 1 over 2 has got to be less than n. So this gives me 3 minus 1, which is 2. 2 divided by 2 is 1. So my n has got to be greater than 1. And I've got to choose the smallest possible. So the smallest possible is 2. So there we go. 2 squared. And therefore this number, subtract 2 squared, has to be 3. And that means this number is a 7. So you see how he got that? So that means A4 is 7. Now, how did I get a 7? Well, we go back and we apply this formula right here. This is my A, and I had to have some sort of n in there. What is n? Well, a minus 1 over 2 is less than n, so that would be 7 minus 1 over 2 is less than n. That means 3 is less than n. So the smallest possible value for n is a 4. That's what goes there. So 7 plus 4 squared would be the number that goes in here, and that is 23. Okay? So now that the numbers are getting larger, it gets more difficult. So that means A3 is 23, but how did I get 23? And that's where this comes in yet again. A this time is 23, so 23 minus 1 divided by 2 is less than n. So that means n has to be greater than, that looks like 11. So I'll choose 12. That's the smallest number I can choose for my n. So this number, subtract 144 is 12, And if you do the math, you'll figure out that number is 167. So this A2 is 167. So we're down to our final step. How do we get 167? Apply this formula one last time. A in this case is 167 minus 1 all over 2 is less than n. That means n is greater than 166 divided by 2, which is 83. N has to be greater than that. So the smallest I can make n is 84. So this number, subtract 84 squared, is equal to 167. And that number, if you do the math, is 7223. So that is my A1. That's the number that I start with. And they want you to figure out the units digit of this number. And the units digit is 3. So number 25, the answer is B.